Hey guys, I am back, and this is going to be the final video for Chapter 8. We're going to go ahead and finish it out. There's just a couple more things I want to go over. The first is sort of talking collectively about these four mechanisms that we've done in the last two chapters. sn1, sn2, E1, and E2. Okay? So we've gone over these in detail, and we have identified certain preferences, certain reaction conditions that are favorable for each one. So ultimately what you're going to be tasked with is you're just going to be given a set of conditions, like a reaction setup, and you, from your knowledge of the preferences, have to be able to predict which mechanism or mechanisms will be present and what products that you'll get. All right? And this can be a little daunting at first, right? The key for this is to, number one, get organized. Make a big table individually or some individual little tables that have quick references for you to remember as you're doing your practice problems, when something's going to be sn1 or when something's going to be E2 or whatever. This will help you as you go along. Plus, the process of writing these tables and summaries really kind of helps things sink in as well. All right? And then this is going to take lots and lots and lots of practice. I definitely encourage you to work those practice problems, not only just sapling, but also back of the chapter. Those will help you out a lot. And as always, if you need me to come by and get me to check some practice problems to see if you're on the right track, I am happy to do so. Let's go through a few of these, though, just to kind of get a feel for how they work. All right? Let's start off with something like this. Okay. So this is a typical type of question that you might run into. All right, you have an alkyl halide here, and we have some sodium hydroxide, and we have some acetone. All right. Again, you always have three major components here. You have the alkyl halide, you have the species that can act as the nucleophile and or base, and then you have the solvent. And they go in that order of importance. Alkyl halide's the most important, solvent is the least important. All right? So what you want to do is take these individually and sort of go back to your charts, go back to your notes and figure out, okay, what is the preferred condition here? All right? In this one, for example, right, we have primary alkyl halides. Ask yourself, what can primary alkyl halides do? Well, we learned that they're capable of being involved in sn2 reactions. They're also capable of acting in E2 reactions. They are not workable in E1 or sn1, so we know those are not possibilities here. All right? So you're going to have sn2 and or E2. All right? Now ask yourself this. This is a primary alkyl halide. They can do both, but does it work better in one or the other? Absolutely, right? We saw that with sn2 reactions, primary alkyl halides worked best, and then secondary and tertiary. E2s, primaries can work, but they're the slowest of all. So that means even though this one is, sort of made that first round of cuts, it's not going to happen, and you're only going to get an E2 reaction. Excuse me, an sn2 reaction. And that means your product is going to be a substitution product. Nice and clean, right? Okay. Well, let's say I changed it up just a little bit. All right, so the only thing here I changed was the sodium salt. Instead of sodium hydroxide, I am using sodium tert butoxide. How does this change the nature of the reaction? Well, what this is going to do is it's going to basically serve as a source of tert butoxide. So I'm just going to, erase the sodium and put that in. Sorry, I have the hiccups. It's really hard to talk over the hiccups. All right. What do you remember about... We talked about this species. What do you remember about this species? We learned that it's a really, really, really strong base, just like, OH minus or OCH3 minus or whatever. But we also learned that it is basically a non-nucleophile. Why? Because it's so big and bulky. Too much steric hindrance. So here you have a case where you have a primary alkyl halide is there, but it doesn't have a nucleophile. Can't have a nucleophilic substitution without a nucleophile, right? So sn2 is off the table. You do have a really strong base, though, so we can get an E2 reaction here. And that's going to be the only thing that we get. So that means we're going to get an alkene product instead. See what we do? We look at our ingredients, we see what's preferred, and we see what's possible. All right, it's very much a systematic process. You just have to get the system down. Let's say you had this. Okay? So what I'm doing here is I've got a secondary alkyl halide in the presence of methanol. All right, let's take a look at this. Secondary alkyl halide. We have, what can the secondary alkyl halides do? Oh my goodness, they can do all of these. They can do sn1, sn2, E1, and E2. Is it ever possible to get all four, you may wonder? The answer is no. There's always going to be something limiting it. But it is possible to get two of them. Let's see what we get. All right, so the alkyl halide's not really going to help us here because it can do all four of them. Let's take a look at the nature of this methanol. All right, CH3OH. Well, first of all, it's going to be a covalent compound. It's not a sodium salt, so it doesn't dissociate, doesn't give you ions. It's working entirely from these lone pairs of electrons on oxygen. All right. If you were to classify this as a nucleophile, how would you classify it? Absolutely right. It's a weak nucleophile. Can this also act as a base? Absolutely right. Very good. It can also be a weak base. All right, so it can equally effectively act as a weak base or a weak nucleophile. It's also going to act as a protic solvent in this reaction as well. Well, what can react here with a weak base or weak nucleophile and a protic solvent? That works for sn1 reactions. It also works for E1 reactions. And what did we say in the last video about sn1 and E1? You always get them together, at least with alkyl halides. So what you would have to do is, first of all, draw the nucleophilic substitution products. And there's going to be a couple of them. Remember, since we have we're attacking a stereogenic center, we get a racemic mix. All right, so those are going to be our our substitution products. Then we also have to draw our elimination products. All right, we have two different types of beta hydrogen here. One of them is between these two beta carbons. These two carbons, one alpha and one beta. And the other one is between those. Okay? All I did was draw what happens when we eliminate the halogen and then beta hydrogens on either side. All right. Are we done yet? No, we're not, unfortunately. What do we always have to look out for the possibility of when we draw these alkene products? We have to look for the possibility of stereoisomers. All right. If we look at this one right over here, you'll see it's tri-substituted, right? We don't have an E or a Z though here because these two methyl groups are identical. So, I mean, switching two identical methyl groups doesn't change anything. So, for this one, you don't have any additional stereoisomers. For this one, however, we see that we're going to have a trans arrangement as drawn. We have a methyl group on this side of the double bond, and then an isopropyl group on this side. It is possible to get a different arrangement of those. We can get the cis. So that would be a fifth product that we would need to draw. So yeah, you can see these can kind of balloon a little bit. I don't want to say out of control. This is entirely manageable, but it can definitely get complex, within a given molecule fairly quickly. All right. But again, just trust the system, trust the process, and you should be able to figure out what you have. I'll just erase everything. What if you had something like this? Well, heck, let's just do that same one. Except let's change the conditions a little bit. My H and 3 got connected there. Sorry about that. Okay. So we have a secondary alkyl halide. They can do everything. All right. So let's take a look at what else we have here now. In this case, we have a sodium salt, sodium methoxide, and we know that's going to dissociate. It's going to give you that. And we know that that's a strong base and also a strong nucleophile. DMSO is a polar aprotic solvent, all right, which works well in both SN2 and E2 reactions. This is be a case where there's actually nothing differentiating whether you had SN2 or E2, so you're going to get both. Remember, if nothing especially stabilizes or destabilizes a particular process, then you're going to get a mixture. All right, since it's SN2, stereochemically, we know we have to get complete inversion. So we're going to get that. And then much like the last one, we're going to get 3 different alkene products. Okay. Now, here's a question. What would have happened instead of using sodium methoxide if I had used sodium tert butoxide? Well, of course, you're absolutely right. In that case, we would have only gotten E2. But since we used a non-bulky species, we get both of them here. All right. Very good. Get lots of practice on that. Get organized with us now, like right now, like seriously, as we speak. Go ahead, if you haven't done so already, make your tables and start really, really learning the conditions here for whatever that are favorable for each one. That'll make your life a whole lot easier. One last thing to go over in this chapter, and that is synthesis of alkynes. Yeah, we can use this stuff to make triple bonds as well, carbon-carbon triple bonds. Specifically, we do this in an E2 fashion. We don't use E1 for this. Basically, what we do is we do the same thing we've done before in E2. We just do it 2 times in a row. These are going to be made using 2 consecutive dehydrohalogenations. Dehydrohalogenations is a long word, especially when you see it written on a tablet using a stylus. All right, they're actually very easy to do. You have to have a dihalide in order to work it, though, and there's actually two different types of dihalides that'll work. All right, you could have something like this. Okay, in this case, what you have is you have two carbons that are right next to each other that each have halogens on them. This is called a vicinal dihalide. And sometimes you'll see vicinal abbreviated as Vic. This will also work, though, with something like this. This is a case where you have two halogens on the same carbon. That is called a geminal dihalide. Often abbreviated as GEM. Okay? So either one of those will work. You need those. You're also going to need a base for this. And when you're doing something like this doesn't just use any type of base. You got to have something really, really strong. There's two types of bases that are commonly used here. One is this. This is called the amide ion, NH2-. And from a salt, you can get it from NaNH2 or KNH2. It is also possible to do this using tert butoxide, specifically in combination with DMSO. NH2-, you can use several different aprotic solvents. For some reason, with tert butoxide, it only really works very well with DMSO, so it's just a little caveat you have to remember. All right. All right, so let me show you how this works. Let's see, let me show you first of all with a vicinal dihalide. Okay, so basically what happens here is exactly what you would think would happen. All right, there's actually a couple of different alpha carbons that can also act as beta carbons as well. So your base, your amide ion in this case, could come in and grab this proton, for example. These electrons could move on down, and that Cl- will pop off as a leaving group. And it gives you this. Okay? Now, if you only had so much NH2, the reaction would actually stop here because you would eventually run out of NH2 before you could get all of this, all these beta hydrogens cleared up. So for that reason, whenever you're doing these type of reactions, these alkyne syntheses, you always need to make sure you have more than one what we call an equivalent. More than one stoichiometric equivalent of NH2-. All right. This is represented by either writing a 2 times next to it or a 2 with EQ, standing for equivalence. All right. But you need more of it. Then your second equivalent of NH2 minus can come in. They can grab this beta hydrogen. These electrons swoop into a triple bond now, and you have your alkyne. All right? So nothing special really there. It's just the same thing that you've already done, just 2 times in a row. Okay? And you see it works very well on vicinal dihalides. You can also do this with geminal as well. Let's say, I don't know, say we have this. right? The only difference is now that the beta hydrogens are not mixing with the alpha carbons. So you get something that looks pretty familiar here. Second equivalent comes in. And boom, you've got your alkyne. Easy peasy. One tricky part about this, whenever you use a geminal dihalide, though, there is one extra little thing you have to look out for. It is actually possible to, when you use a geminal, to get product mixtures of alkynes. If you had something like this, for instance, let's see, something like that, right? In this case, you see you have actually those two beta hydrogens that we take off. There's a couple of them over on this side, and there's a couple of them over here on this side. All right, and so whenever you do that, that means you could form that triple bond between these two carbons, or you could form them between those two carbons. And you see these are two different alkynes here, definitely, so you get both of them. You do not have to worry about cis, trans, or EZ with alkynes. That is not a thing. I'll explain that more when we get to the alkynes chapter. But this is something you do have to worry about with geminal dihalides, so just be on the lookout for it. All right, that is the end of chapter 8. A lot of learning here, and as you can see, we're knee-deep in reaction chemistry now, right? So hopefully you guys are getting the hang of it, getting lots of practice. Keep working at it. If you have any problems or questions, please let me know. All right, until then, I hope you have a very good day. Bye-bye.